Swayam Prabha. Digital India. Educated India.
Let me try to continue my discussion in the area of piezoelectric ceramics. We have been talking about the different coefficient used in piezoelectric or piezoelectric phenomena. This we have already discussed, the strain coefficient as well as the charge output coefficient and then the voltage coefficients. We will define them at a later stage, how exactly it comes up. And also another very important parameter is the coupling coefficient, which is basically the energy efficiency of the system of that particular material, either from the electrical to mechanical or mechanical to electrical. Well, keeping those things in mind, this we have already discussed, the coupling coefficient, that is basically a ratio of the two energy terms. There is one more important aspect to be noted for piezoelectric effect. We are basically applying a stress and generating a polarization or a voltage. Now, if you apply a instantaneous stress at certain time and then try to maintain that stress at a constant value, you do not change the stress, then the polarization which is generated does not remain constant over a period of time. In fact, it decays slowly or the voltage drops down. So, it is basically a dynamic process under which you get this effect of piezoelectricity, that is you have to continuously vary the stress so that you get a continuous voltage. In fact, most of the time what we do, we actually apply a sinusoidal stress like in vibrations. Okay. If you are vibrating, there is positive stress, that is the compression and then tension or tension followed by compression, and so that under that condition you get almost a polarization, development of polarization or development of voltage in phase with the applied stress. So, if you really want to use, one really wants to use the piezoelectric behavior of any material and make a device out of it, it has to be designed in such a way that there is a variable stress and or in reverse way the polarization also will change. Polarization also can be varied so that the stress is generated in phase with the polarization or applied electric field. So, that is in fact that is one of the reason most of the piezoelectric devices are actually operating under alternating field, not under direct field. Direct field applies only when there are certain applications. There are certain applications where a direct field applies or direct voltage is generated, but that is instantaneous. You cannot maintain that voltage over a long time. So, coming back to hysteresis, because we have discussed these things in details, why the hysteresis comes up, what is the basic origin of a hysteresis curve or polarization versus electric curve field. It is basically because of the domain structure. since all piezoelectric are supposed to be ferroelectric material as well. So, we have a domain structure here as well, and we have a hysteresis curve. So, this hysteresis curve is also a very typical characteristics of piezoelectric material as in case of ferroelectric material. In fact, they have the ferroelectricity in it. So, you have a virgin curve, that means once you start from the 0 field initially, it follows this curve and then goes to the saturation point when all the domains are aligned parallel to the electric field, and then if the electric field is reversed, then it does not come back to the 0 polarization at 0 field, but there is a remnant polarization. And then you have a coercive field in the negative direction to neutralize it, and then it follows and goes to saturation in the negative direction. So, that is the hysteresis curve we have with piezoelectric material as well as in case of ferroelectric material. However, we have a additional feature here, that is change of strain as a function of electric field. So, in ferroelectricity we did not have that effect. So, we did not have this kind of a curve. Here, since we are talking about mechanical energy or mechanical stress generated as a not only polarization, but it also generates a mechanical strain, and one can find out what is the strain applied, what is strain generated as a function of electric field. So, it is obviously as initially, that is again the virgin curve, that is from the initial stage the poled material, of course these are all poled materials. And so, in a poled material, if you apply an electric field, the strain increases following this dotted curve. Then if the electric field gets reduced, strain gets reduced, it comes to 0 once again following a kind of hysteresis pattern. You have a remnant strain here, and then there is a coercive field to neutralize the remnant strain. However, there is a something different happens here when the electric field goes further in the negative direction, the strain actually increases. Strain does not go below, or there is no strain, negative strain that way. So, the strain again increases, and you can get a reverse direction also in the same manner, and then it goes there. So, it is a kind of butterfly curve. So, against a hysteresis curve in polarization versus electric field, in the strain field or the strain domain, you get a slightly different behavior. Strain does not go negative. So, you have basically a kind of butterfly curve which is generated. So, all the time you have a positive strain. So, this is the difference here, and the additional feature what we get in a piezoelectric material as a function of applied field. Well, with this descriptives or whatever descriptions I have given qualitatively, let us try to understand what are the different kind of coefficients and what is their mathematical representation, or mathematically how one can relate to different parameters. Application of mechanical stress induces dielectric polarization within piezoelectric material, and thus sets up a voltage across the device, that we have already seen and we have discussed. So, that is called direct piezoelectric effect. Stress is a vector quantity and therefore induces different magnitude of voltage in different directions. So, this stress is not a singular stress, it has a different components, because we will see later on, if you apply a stress in one direction, it has its effect on the other directions as well, as you have seen in the very first picture, there is either a reduction in the diameter when you apply tensile force, or if you have a compressive force, the diameter gets increased. So, there is a Poisson's effect, and therefore, the strain has a different connotations. It is not always in one particular direction with respect to the geometry of the specimen or geometry of the device. So, we have to consider different directional properties both for the applied voltage as well as the applied the resultant strain or vice versa. So, the reverse effect is also there, which I have mentioned earlier. The reverse effect is also possible. Application of voltage generates stress and also strain. So, stress and strain are actually related terms by Hooke's law. We will discuss that in a few minutes. So, it generates in different directions, and therefore, a converse piezoelectric effect also exists. Both stress and polarization being vector quantities, the coefficients which relate them are quite complex in nature, and in fact, they form an elements of a tensor. Okay. So, these are the coefficients which correlates mathematically correlates the mechanical stress or strain to the dielectric polarization or the voltage. These coefficients are not singular numbers, they are a set of complex numbers, set of large numbers, and depending on the different directions in which the stress is generated or the voltage is getting generated. So, they form actually a tensor, and we will see how many of the elements are there in the tensor. Mathematically, the relationships are represented as follows. There are different ways to correlate them. For the direct effect, we say Dij, d is the flux density, and small d Ijk. So, there are 3 orthogonal directions. So, these are Ijk, and that is the coefficient, and the stress pattern, stress is x j k. So, the x, that is the stress is generated or stress is applied in one particular direction, and the flux density or the voltage may appear on different directions. So, that is why we have the subscripts I j or I j k and then j k. We will come up with little details of these things. The converse effect can also be related like that, where stress is the x I j is d k I j. So, it is actually the transposed matrix. D is actually a matrix now, and you will find E k is the field. Okay. So, d I j k, d k I j is actually the transpose matrix of d I j k. So, it can be written at k I j, and E k of course is the electric field vector in the k direction. So, if you have a k direction and then we are measuring the stress in the I and j other directions, then this particular type of coefficients will appear. Where, as has been explained just now, where d I j k its unit is coulomb per Newton, is the piezoelectric coefficient of the third rank tensor. It is called third rank tensor. We will see what is that third rank tensor. D is the charge density, or also the flux density sometimes called, and x is the mechanical stress and E is the applied electric field. So, these are the parameters which have been used in the two equations just presented. The subscript T, superscript T, this T which again has been explained just now, is refers to the transpose matrix of Dijk. So, Dijk transpose becomes Dkij. The unit of this transverse piezoelectric coefficient is meter per volt. Okay. So, it is basically how much the extension as a function of unit volt. Now, the signs of the charge density, that is Dij and that of xjk depend on the direction of the mechanical and the electric fields respectively. Therefore, the piezoelectric coefficient Dijk can be either positive or negative, okay, because we have different possibilities of the stress as well as the strain, the flux density. Now, how these different subscripts come? The subscripts come from this kind of a consideration. In order to designate the axis in orthogonal directions, in fact, one can have a orthogonal system of representation in the solid geometry like situation, where x, y, z or x, y, z are the axis, orthogonal axis, and they can be also represented as 1, 2, 3 in another form of notation. Now, when we apply an mechanical stress on this cube, for example, that have a different kind of consequences. The stress can be normal to any of these axes, either z axis or x axis or y axis. So, this can be called as normal stress. However, if there is a inclined stress and at an angle, that will have different kind of components in different directions. Sometimes the stress can also be may not be a normal stress, but it can be used as a shear stress. So, one considers the shear modulus, and in the normal stress one considers the Young's modulus to correlate stress and strain, whereas when there is a shear stress, the coefficient is different and one has to take into account the shear modulus of the material. So, there are this kind of rotational stress surrounding this particular axis, that means it is on the surface of this, not perpendicular to the surface of any of the surfaces. So, this shear stress acts on the surface, right, and they can be represented by a circular array like this. And there will be 3 shear stresses, 4, 5 and 6. Okay. So, this is how all the stress systems, stress tensor can be represented. Okay. So, there are 6 elements of the stress, 1, 2, 3, 4, 5, 6. 3 of them are normal stress and 3 of them, another 3 are actually shear stress. So, this is how actually we will represent and we will find out the equations as well as the coefficients, a series of coefficients in different directions. To link the mechanical and the electrical quantities, double subscripted coefficients, as for example Dij, are normally used. Okay. The first subscript indicated in the indicates the direction of the excitation, and the second subscript is actually second subscript denotes the direction of the system response. I will just correct that. The first subscript then indicates the direction of the excitation, that is, it may be applied voltage or applied stress, and the second denotes the direction of the system response, how it responds. So, dij, I is the direction. If it is 1 2 for example, then 1 represents the direction of the applied stress, and we are measuring the response, the electrical field generated in the second direction, 2 directions. So, this is how actually the notations have been used. The most important coupling modes are 3 1, minus 3 1 and minus 3 3, that is I equal to 3 and j equal to 1, and or I equal to 3, j equal to also 3. So, 3 3 actually is the normal mode, whereas 3 1 becomes a CR mode. So, these are basically the how we denote a coefficient, a piezoelectric coefficients. Well, there are a few more things to discuss. That is, in the minus 3 1 mode, the stress is applied in the direction of the perpendicular to the Pauling direction. Here Pauling direction is a reference, and so 3 directions as if it is in the z direction. So, assuming that the Pauling direction is in the z direction. So, you are applying a stress in the perpendicular to the Pauling direction, right, and 3 1 applies if the electric field is along the polarization axis, direction 3 again, but the strain is along axis 1, orthogonal to the polarization axis. Okay. So, 3 basically depends or refers to the axis parallel to the polarization axis, the way the material has been poled. If it is a cylinder, normally if it is a cylindrical specimen, then it is the c axis, which is the normally is the Pauling axis, and that is also here will be referred to as the number 3 axis. In the 3 3 mode, a force is applied in the same direction as that of the Pauling direction, as for example compression of a piezoelectric block that is poled on its top and bottom surface, once again the same thing, and we are measuring the voltage generated also in the 3 direction, same direction. Here 3 1 for example, it is we are measuring the voltage in the orthogonal direction, a perpendicular direction to the top and bottom surface. Okay. So, this is how the whole thing is designated. This is the example, what exactly means by these are the modes which are normally used in many devices, and they are actually more important modes. Here to exemplify the situation little clear in a clearer term, what we have taken is a strip. This is not a cylinder, but a strip, a rectangular strip of a piezoelectric material, and the directions are like this. This is 2 direction, this is 1 direction, and the vertical direction is 3 direction, or the z axis, x axis and y axis you can say. Okay. Now, this is what we call the 3 3 mode, where we are applying the stress along the 3 direction, the z direction. Okay. We are applying the stress along the z direction, it is a compressive stress, and then we are measuring the voltage also along the same direction between the 2 bottom and the top surfaces. So, the axis actually is parallel. Okay. So, the direction of the application of the stress and the measurement of the voltage is same. Okay. It may be reverse also, that means, if we apply a voltage in this direction and try to measure what is the deflection or the change in change of dimension along the same axis, then this becomes a 3-3 mode. Okay. Whereas, the same strip, if it is stressed differently, I mean we are still measuring our voltage between the top and the bottom surfaces, whereas applying the stress in a orthogonal direction. Okay. We are now trying to pull along its length, okay. And then also you will generate some voltage here, because this also has a component because of the Poisson's relationship. So, if you apply a stress on this, actually there will be a compressive stress between the top and the bottom surface. So, just like this here. So, these are there has some kind of a similarity. Either you apply a compressive stress along between the along the top and bottom surfaces, or apply a tensile stress along this. Okay. So, that will also result in a compressive stress between the two surfaces here, two parallel surfaces top and bottom. So, this becomes your 3-1 mode. Okay. We are applying voltage, one can say this is 3-1 or 1-3, depending on which kind of parameter or which kind of voltage, whether we are measuring the voltage by applying mechanical stress or the reverse of it. Okay. So, if we are 3 mode is this one, which means 3 is the first one. So, we are applying the voltage here and measuring the stress, okay, measuring the stress. If it is 1-3, if this becomes 1-3, then it is reverse. We are measuring the we are applying the voltage, sorry, we are applying the stress along one direction and measuring the voltage in the 3 direction. So, one can have 1-3 also. So, there are many possibilities, there are many different combinations are possible. Accordingly, you have different kind of different coefficients with different subscripts. So, conventionally -3-1 mode has been the most commonly used coupling mode. However, -3-1 mode yields a lower coupling coefficient K than the 3-3 mode. Okay. So, 3-3 mode and 3-1 mode has been described here, but if given an option 3-3 mode is much better, because the 3-1 mode yields a lower coupling coefficient. So, the energy conversion is little low in case of 3-1 mode compared to 3-3 mode, because both of them are parallel to each other. So, this is a kind of interpretation, physical interpretation of these modes or of these subscripts. Sorry. What happened? Right. We have a little complex description of the same thing which we have discussed just now. For that, we consider in a slightly different way. The piezoelectricity is a combined effect of dielectric and mechanical behavior that we have been mentioning all along. According to the principle of dielectrics, one can write this equation. This that is we have seen in case of a normal dielectrics, right. This is d, the flux density, is equal to epsilon, the permittivity, and the electric field. So, the flux density arises because of the application of the electric field, and the coefficient is the proportionality constant is actually the epsilon or the permittivity of the material or the dielectric constant. So, higher is the dielectric constant, flux density will be high for the same applied field. And since we are talking about a mechanical system as well, because two things are different, they are to some extent compatible, but they have their own identity. So, not only dielectric behavior has to be represented, but also the mechanical behavior we have to understand, and we know Hooke's law where stress and strain has been related by an Young's modulus. So, basically the proportionality constant, as we know, is the Young's modulus, but this Hooke's law has been here, it has been written in a slightly inverse manner. That means, this is the stress is proportional to this is strain, this S is capital S is strain, and T is the stress. Okay. So, Young's modulus is actually stress by strain by stress, okay. Whereas here this proportionality constant small s is known as the compliance. So, it is the inverse of Young's modulus. It is the inverse, S is the compliance, which is the inverse of the Young's modulus. So, when all the terms have been explained here, d is equal to the dielectric displacement, epsilon is the permittivity, capital E is the dielectric field, capital S is the mechanical strain, this is mechanical strain, and S is the compliance, is the inverse of Young's modulus, and inverse of Young's modulus, and T, capital T is the stress, mechanical stress. So, all these parameters are involved when a piezoelectric system is functioning. All these parameters are actually involved, and some of them are coupled together, and that is what makes our life little complex. So, one can write a in the form of a tension notation, considering that the direct and the converse piezoelectric effects and the coupled equations to describe the phenomena. This phenomena is described by what we call a coupled equation, because in the same system, in the same material, we have two different effects of two different parameters. Okay. One is the stress T, and another is the electric field. So, both these things are operating on the same system. So, you have this one, what is the strain. If you want to find out what will be the strain, that means deformation of the material, it arises both because of the application of stress here and also application of the electric field. So, both these things are simultaneously operative, so that a strain is generated in a particular direction. So, this is the kind of a coupled equation for expressing the stress strain sensor, strain tensor. Okay. So, this is the strain, and then if you talk about the electrical effect, then you have dielectric flux density d also generated from stress, and it is also a effect of electric field. So, in both the cases, whether this is stress and electric field, both is generating a strain, mechanical strain, and also both of them can generate a dielectric displacement of the flux density. So, that is why they are called coupled equations, and these are the two effects. One is the direct piezoelectric effect, other is the inverse converse piezoelectric effect, where d is this one, d is a coefficient proportional, some kind of a proportionality constant is the matrix actually. This becomes the third bracket, or the square bracket actually represents the matrix, and the second bracket here represents a tensor quantity. So, the direct piezoelectric effect, and dt is the transposed matrix for the converse piezoelectric effect. The superscript E is here, E indicates either 0 or a constant electric field, that means stress strain at constant electric field, which is actually a coefficient. And then we have the superscript T, also there is a superscript T here with the epsilon superscript T, that indicates a 0 or a constant stress field, and the superscript T stands for the transposition of the matrix, which has been already mentioned. So, these are the basic two equations which describes the overall phenomena of piezoelectricity. Okay. One is the direct piezoelectric effect, another is converse piezoelectric effect. The lower one is the converse piezoelectric effect, and the upper one is the direct piezoelectric effect. Now, this can be expanded. This can be expanded to a large extent, and there are many symmetry elements, or because of the symmetry of the geometry, many of the coefficients are actually 0, but there are some real values here or finite values in this. These are one set of coefficients, and these are another kind of coefficients. So, in fact, there are 3 different coefficients. One is S coefficient, or the strain coefficient, this is the piezoelectric coefficient D, and this is the dielectric coefficient, okay, epsilon. So, that also have different directional properties. Okay. So, here you have, we have seen earlier, this is the strain. Strain can have 6 different axes, along 6 different axes. These 1, 2, 3 are the normal strain, and 4, 5, 6 are the shear strain. So, these are 6 element tensor here, and then stress, sorry, there is a missing link here, it should be T6. These are T6, this is 0, 0, 0. Okay. These are, I think I made a mistake, I corrected somewhere, but it has not been shown. So, this is also T1, T2, T3, T4, T5, T6. So, these are along the 6 directions, and the electric field is only along 3 different directions. Okay. The applied electric field is in 3 different directions. We are not applying electric field along any surface. So, electric field is applied along the orthogonal directions only. Okay. So, these are the total, one is the direct, and there is the converse effect. Now, all of them, all the coefficients are really not effective. Okay. Some of them, as you can see in all these matrices, some of them are effective and some of them are not, and that of course, it is a particular symmetry element present, the strain charge relationship for the crystals with tetragonal symmetry. Okay. When there is a tetragonal symmetry, this happens. If the structure is different or the geometry is different, then of course, others will be operative, this may not be operative. So, it all depends on the in an ideal case, all these 6 into 6 36, and here 6 into 3 18, there are 9 here 3 into 3, and there again 6 into 3 18, all of them will be have a finite value, but most of the cases, because of the particular symmetry, cylindrical symmetry or a tetragonal symmetry what we have mentioned here, because of that some of them do not operate or do not appear actually. So, we have seen here, we are earlier discussing about 3-1 mode, this is your D3-1 mode and this is your 3-3 mode. So, displacement as a function of applied field as well as stress. Okay. But the first equation represents the relationship for the converse piezoelectric effect, and the later, sorry, I mentioned differently, this is the direct and this is the converse. Okay. It has been reversed here. Well, with this little background, let us go to what are the things we can design with a piezoelectric or piezoelectric material. This is what we call a piezoelectric bimorph. Okay. It is actually a thin strip. In fact, it is not a monomorph, it is called bimorph because there are two strips put together. Okay. One is the top one and there is the bottom one. Though there are two separate strips and they have been put together. The difference between them, of course, the dimensions are same. It is a rectangular strip, very thin rectangular strip with small thickness, maybe within a millimeter or so. And the major difference here, you can see they may have two poling directions. Okay. Both of them have been poled. So, they will have a poling direction and the resultant polarization direction here is this one. For the bottom one it is pointing downwards and the top one also is pointing downwards. So, when we are putting them together, it actually we are putting them with the use of a glue, okay, some adhesive, sometimes a metal can also be used in between, but when we are putting them together in such a way that in both the things, both the strips, the polarization axis is same, they are pointing downwards, and we apply a voltage across this is a positive voltage and the this is the negative voltage on this side. If the polarization axis is like this strip will expand in this manner, will extend, its length will increase in this manner uniformly because of this particular characteristics or relationships. So, this is positive and this is negative and it will expand in this direction. Whereas, in the top case you can see here these polarization directions are different. So, they have been put in such a way, they have been while they have been glued together, they have been put in such a way that the polarization axes are different, okay, one pointing downwards, another pointing upwards. In such a situation, one will try to expand, the other will try to contract. Okay. So, this lower one is trying to extend just in this particular case. So, here one also both of them are trying to expand along the length. Here the lower one is trying to extend or expand, whereas the top one is trying to contract. As a result, what will happen? It will bend, the whole strip will bend. So, just by designing the configuration, the way we configure the materials, one can have two different effects, and both of them have their implications. For example, by this process if you apply a very high frequency, it will basically try to vibrate. Okay. Once you put to the positive field here, negative field on the other side, and next moment if you change, it will bend in the opposite direction. So, as a result, if you have a applied voltage, high frequency applied voltage, this whole thing will start vibrating and it can generate noise. or a particular frequency, not necessarily noise, but a sound wave. A audible, depending on the frequency, a audible sound can be made, a ultrasonic sound can also be generated. So, this is a very useful design for utilizing the piezoelectric effect of a material. Here of course, this also has its own utility. It is expanding or contracting. Okay. If you reverse the applied field, it will try to contract. So, there is a, instead of a vibration, you are getting a linear movement, expansion or contraction, and that can also be utilized very precisely, and these movements are very small, sometimes few microns or tens of microns. Okay. So, if you need that kind of translation, so actuators, kind of actuations, one can make this kind of a system or a device where piezoelectric actuators can be designed for many different purposes, for small length of movements. Well, this is another kind of design. This is another kind of design where the piezoelectric ceramics have been sandwiched between two metal plates, very thin layer of metal plates. However, there is a gap in between. Okay. So, this is also another, this is basically to enhance the vibration or increase the intensity of the, it is a kind of amplification one can generate by applying these metal plates. Of course, metal plates also have another very important usefulness, because this is expanding or contracting and vibrating depending on what kind of electric field one applies, and therefore, there is a lot of mechanical stress gets generated in this thin strip of ceramics. And ceramics, as is well known, it is basically a brittle material, and it has its own problems of crack propagation and so on. So, when you are dealing with ceramics and also trying to mechanically stress, you have to be little careful, so that it does not break, it does not crack, because it cracks almost instantaneously. That is the character of a brittle material. So, it is also acting as a kind of reinforcement. Metal can withstand much higher stress, and it is a plastic material, it is not a brittle material. So, metal it is kind of a reinforcement for the metal, for the ceramics, but at the same time it also acts as an amplifier. So, if you want to generate a vibration or just a minute, generate a sound, just in case of a loudspeaker or that kind of situations, this kind of metal acts as a amplification, provides an amplification factor. So, there are two different designs, and with two different names have been given. Only thing, the ceramics is same, but the metal configuration is slightly different. Now, here we have shown only one layer of ceramics, piezoelectric material, but one can also have a multi-layer piezoelectric material. We will come to that later on, what are the main applications of the piezoelectric materials. One of course is a sensor, the other is actuators. These are mostly different sensors and actuators, and the amplification or the sensing capability or the actuation capability can increase by manifold by multi-layering. Earlier we have seen in a multi-layer capacitor, the effectiveness of a capacitance or the overall value of the capacitance can be enhanced by multi-layering with a sandwich structure. In between you have electrode, metal electrodes. Here also very similar amplifications can be done. You can use very thin layers of piezoelectric material and then screen printed metal films. So, multi-layer structures are also used quite extensively for enhancing the actuation property, particularly the load bearing property. The load bearing property, because when you are trying to actuate in the sense you are trying to physically move something, physically change the dimension, physically change the position. So, you have to move different kind of loads. Okay. You can you need different kind of mechanical stress. So, that mechanical stress gets enhanced. One is the vibrational enhancement, that means the amplitude of vibration. So, that is one kind of enhancement or amplification. The other thing is the amplification of the total load bearing capacity, that means how much load it can move, okay, or physically move from one position to the other. So, that can be enhanced by multi-layering. So, although the property the inherent property of the material remains same, but just by designing a different configuration one can enhance the property to a large extent. So, these are some of the ways one can use piezoelectric materials. Well, we are coming back to the material property once again. We have not discussed too much about the material so far. Generally we have discussed the properties and how one can design, what is the relationship between the polling direction and then how a bimorph can be bent or increased in dimension longitudinally and so on. So far as the material is concerned, the best material, the most important material available to us is once again a perovskite compound. Earlier we have seen barium titanate as one of the very useful ferroelectric material, ferroelectric ceramics. Here is another perovskite material, in fact a compound or a solid solution of two perovskites. One is lead zirconate, another is lead titanate. Both of them have perovskite structure. So, there is a complete solid solubility. So, you can in fact have lead zirconate on one side and lead titanate on another side. This is a phase diagram in fact. So, it is basically a phase diagram. This is lead zirconate, 100% lead zirconate, and this 100% lead titanate. So, you have a complete solid solubility. You can fix the composition at any point on this axis, okay, whether it is 25%, 50%, 70% and so on. Now, this is basically the phase diagram and it represents various different polymorphic forms of this compound of this particular solid solution. If you take pure lead zirconate, you have this is the ferroelectric phase, it is stable over a composition range. You can add about 50% of around 50 mole percent of lead titanate and you have a rhombohedral. This is the rhombohedral ferroelectric phase. Okay. So, the ferroelectricity, as you remember, is very intimately connected to the crystal structure. So, this rhombohedral structure is actually the ferroelectric phase. And if you increase the temperature, this is the temperature axis. So, if you increase the temperature beyond this line, then the ferroelectric get lost. So, you have a QD temperature which locus is like this. At for 0% lead titanate, that means 100% lead zirconate, the QD temperature is around little less than 250, is around 240 to 45 degrees, right. Whereas, if you add lead titanate, continuously, you can see the QD temperature increases and it goes up to almost very close to the 500 degree centigrade, right. So, the QD temperature changes Curie temperature changes by adding more and more lead titanate to lead zirconate. However, throughout this range there is a ferroelectric phase, okay. There is this also a ferroelectric phase, there is a ferroelectric phase here, and there is a Curie temperature. Now, this region is the cubic phase. Okay. So, since the cubic phase is symmetric phase, it cannot have ferroelectricity or piezoelectricity. It is actually cubic phase and paraelectric phase. Okay. So, it is a simple dielectrics or a linear dielectrics, whereas below this Curie temperature it is both ferroelectric and also piezoelectric. Now, there is another point to be noted here, this particular boundary. Okay. There is a phase change here as a function of composition. This is rhombohedral phase and this is tetragonal phase. Both of them are ferroelectric phase, no doubt, but the structures are different. Okay. This is a rhombohedral phase, this part is rhombohedral phase and this part is tetragonal phase, and this is what we call the boundary between rhombohedral, where the rhombohedral phase is changing to tetragonal phase, and this particular boundary is called morphotropic phase boundary, and that has a very important connotation on the property of the ferroelectric or the piezoelectric material, particularly the lead zirconate and lead titanate, solid solution of lead zirconate and lead titanate, which is in short called PZT. Okay. So, it is the PZT or sometimes called PZT. This is a very important piezoelectric material, and it has been extensively used in industry for many different devices. We will discuss little bit of that in the next class. Okay. So, for the time being, goodbye and thank you.